Okay, welcome back. Hope you had an opportunity to take a break and also check out the poster session. So keep in mind during each of the breaks, you can navigate through the scene and find the poster session. So please make sure that you visit those at some point during the day. And so with that, hope you enjoyed our section 4, which talked about training opportunities and training challenges when it comes to moving forward the field of persistent nutrition. Now I'm going to talk about, we'll move into section 5, which will be really talking about some of the computational analytics and data analytics that we've been referring to throughout this morning. So I'm going to start off the session talking about what do we mean by precision nutrition and system science, data science, and computational analytics. So next slide, please. So when we talk about persistent nutrition, it basically means better tailoring diet and nutrition to the complex systems that affect and comprise each individual. So these complex systems that affect, how your body processes what you put into your body, and ultimately what happens to your health, and not just in the short term, but in the long term. And these are all very complex systems that mediate this. Next slide. So what do we mean by a system? We've tossed around this word quite a lot. So we know that individuals do not exist in isolation. They are, in fact, actually part of many different systems. So people themselves are biological systems and physiological systems, but they're part of social, political, environmental, and economic systems. Next slide. So basically everything in the universe is a complex system. So we have transportation systems, ecologic systems, manufacturing systems, meteorologic, financial, and aerospace systems. As you've probably seen, system science and computational analytics have really transformed many of these other fields. So for instance, whenever you watch a weather report, you see the weather map. That in fact is the output of a computer simulation model, which basically takes data from really many different diverse sources, such as barometric pressure, temperature, cloud cover and movement, what the tidal waves are doing, et cetera, and merges together with a computer simulation model to present a weather map and your weather forecast. Imagine years ago, before we had these types of computational analytics, how would people understand the weather? They might look at the moon or the stars and see what the cows happen to be doing at the time. And maybe they could predict or forecast the weather maybe an hour or two in advance, potentially a day in advance, but really not much better than that. So we've really come a long way when it comes to computational analytics and fields like weather or meteorology or air traffic control. So the question is, can we do the same thing in nutrition? Next slide. So one part of computational analytics is computer modeling. So for instance, computer modeling can help better understand and address complex systems. So whenever I mention to people that I'm a modeler, without putting in the word computer modeler, they look at my clothes and my distinct lack of fashion sense and say, oh, no, you're not a model. And then when I say computer model, they might think of the left side where, you're carrying a computer and say, okay, I'm modeling this computer. But it's actually the right side of the slide, which is using computers to basically do different types of analysis to really represent what's actually going on in real life and get a better understanding. And basically, it's helping facilitate systems approaches. Because as we know, technology in itself is neither good nor bad. It's how it's applied and what can it help accomplish. And technology, there's a real opportunity to help facilitate systems approaches and a better understanding of precision nutrition. So next slide. So when we say systems approaches, well, what are the dangers of not using systems approach? Well, I've illustrated on this slide 5 different dangers. So one is coming up with band-aids rather than solutions. So we've seen this in the fields of all types of health fields, but also in nutrition. And I want to add, there's been a lot of great work that's been done in nutrition for many years. We've just been hampered by, in some cases, the lack of data. In some cases, science needs to progress, and we need to have a better understanding as time passes by. So I don't want to say this in a way that suggests that nutrition research has been problematic in the past. We've really made some great strides in terms of nutrition research, but these are some of the challenges that we've encountered when it comes to not being able to apply systems approach. So when we talk about band-aids rather than solutions, we might see, okay, here's a problem, and let's try to address one aspect of it so that we don't necessarily see the problem again. And unsustainable solutions is another issue, or missing secondary and tertiary effects. And this can be both positive and negative. So when it comes to diet, a positive dietary intervention can have reverberating effects throughout the entire lifespan of a person. Because if you think about it, you can affect the health immediately and also subsequently affect the impact of the risk of chronic medical conditions. So you can miss positive effects, but you can also miss negative effects and have unintended consequences. And also, you can have a situation where you expend considerable time, effort, and resources from trial and error if you don't understand the complex systems. So I did get some feedback that I just want to make sure that everyone can hear and that the volume is loud enough, but I'm going to continue until I'm told to stop. So hopefully everyone can hear me. Next slide. So we can use computational approaches that to help better understand and address these complex systems. As I mentioned, we as humans, we can understand direct effects. So, you push something and you push a chair and the chair moves. So you can see that. You say, okay, I caused that movement in the chair. Secondary effects can be more challenging. Tertiary effects can even be more challenging. And then once you get things to being very complex, then it's very hard for us, no matter how much experience you have, no matter how much training, no matter how much logic you may have, it's difficult to really untangle these complex systems. So this graphic essentially shows this. If you see on the left side, individuals can struggle really understand these complex systems. So you can have different types of computational approaches and data analytics to put order to these things and help you understand, okay, this is how things are connected. And it helps you understand how you think about these complex systems, and it helps translate what you think about them to other people so you can have shared understanding of complex systems. So next slide. So there's really, when you talk about analyzing systems and situations, there are two general approaches. One is the top-down approach. So you look at, say, for instance, a sea of data or a sea of information, and it's as if you were floating and above the 10,000-foot level, and you look for patterns. You look for, what's associated with what are the correlations. This can be very helpful in the discovery phase when you're trying to narrow down what you want to look at. So, for instance, you might do a large population study and say, okay, what's correlated with these different aspects of nutrition? But it doesn't really get at mechanisms and cause and effect. Next slide. So the other approach is a bottoms-up approach where you actually try to recreate the system. You try to recreate what's happening. So you try to build the system. This way, you can better understand what's happening. So there's the aphorism that you can't understand something unless you actually can rebuild it. And so when we talk about computational analytics, they really go in both directions. One is a top-down approach to look for patterns and associations, and the other is the bottoms-up, where you really actually try to rebuild what's happening. You need both. Like if you overemphasize the top-down approach, you really will start ascribing mechanisms to things which may just be correlations or associations or even just red flags, or red herrings. If you just use the bottoms-up approach, you may not be able to get at some of those general associations, or you may be tackling parts of the system which may not be priority parts. So you really need both. So next slide. So here are some examples of some of the computational analytics that our team has used. So one is building this virtual infant model. So simulating infants and their activities. So we've developed an agent-based model which simulates real infants, and so these infants have these embedded metabolic models, and infants each day go through different types of activities. So they might burn activities by their motion or movement, they wake up, go to sleep, and then they have different types of feeding patterns depending on what their caregiver may give them. So that will determine how many calories go into their body, how many calories are burned, and then that will translate to different effects via the metabolic model, such as weight gain or weight loss. Next slide. So here's an example of a study in which we used a virtual infant to evaluate different formula feeding guidelines and see what the impact of that might be. And this was published in the journal Pediatric Research. Next slide. So this is just a quick hitter in terms of what we found. So we found that when you actually follow these formula feeding guidelines, even if you just follow the minimum recommended amounts of formula feeding, that can still lead to situations of overweight or obesity. And this is just the graphs of, you can see on the x-axis infant age in months, and on the y-axis what happens to their body mass index or the BMIs. So you can see over time it actually increases in many of these virtual infants, which suggests that following some of the existing guidelines may actually lead to obesity and overweight, which then suggests that we may want to take a closer look at these guidelines. Are they actually tailored more precisely to each of the different infants' needs? Next slide. We found a similar situation when it comes to testing different complementary feeding guidelines. This was published in the American Journal of Preventive Medicine. Next slide. Again, similar situation where when you actually follow these guidelines in terms of when to introduce solid food for infants, you can actually have overfeeding, even if you're changing or trying to adjust it from day to day. And the challenge here is that a lot of the guidelines were developed for the population in general, and they were generated, looking at different associations and correlations, some of the scientific evidence, but our virtual infant model suggests that more tailoring can be better in terms of helping manage the body mass index for infants. Next slide. And here's an example of work that we've done across the broader population. So the virtual population for obesity prevention, VPOP model. This is an agent-based model in which we represent entire cities like Baltimore or New York City, San Francisco, or Philadelphia. Next slide. So these agent-based models include, all of the key locations such as food sources, households, workplaces, schools, physical activity locations for all the people in the population. Next slide. And each person within the population is represented by a computational agent that has all these different characteristics like age, gender, race, ethnicity, socioeconomic status, just like real people. So for instance, the Baltimore model will have over 1 million of these computational different agents. And next slide. And each of these agents then goes about their daily business, different types of activities like having breakfast, lunch, dinner, moving out throughout the city, interacting with different agents, engaging in physical activity. Next slide. And each of these individual agents, just like real people, have their personalized models within them. So whatever they eat and whatever types of physical activity they may have is then translated to changes within their body, including the risk of different chronic medical conditions. Next slide. And so here's an example of how we use this virtual VPOP agent-based model of Baltimore City, Philadelphia, and San Francisco to evaluate the effects of a sugar sweetened beverage warning label on health and obesity prevalence. Next slide. And quickly, this just shows the 3 different cities, Baltimore, Philadelphia, San Francisco, and different sugar sweetened beverage warning labels, and on the y-axis, obesity prevalence. And just the quick bottom line here is that you see differences in changes in obesity prevalence from city to city because cities are different and their environments are different and their populations are different. So you can't expect the same specific intervention or policy to have the same effect across different cities. So next slide. So in summary, nutrition and health involve complex systems. Not everyone responds to different nutrition and diets in the same way. So precision nutrition is better tailoring diets to systems of interest. Computational analytics and approaches such as AI, machine learning, and modeling can help better achieve precision nutrition. However, they really need to properly account for and address these complex systems that affect and are affected by nutrition. So with that, next slide. Just wanted to give the FICOR team some credit for some of the studies that I mentioned. Very valuable team with many coming from many different disciplines, so it's a joy to work with them. And next slide. And this is just some of our my contact information if you want to reach me or reach our FICOR team. So with that, I'd like to segue to our next set of speakers, Dr. De La Haye, Dr. Hammond, Dr. Surya. They're going to give some examples of how you use some of these computational analytics and data analytics, such as social network analysis and AI or machine learning, to better address different issues, ranging from general health issues to specifically nutrition issues as well. So please join us for these next set of presentations. And then after that, we'll have a Q&A. So this will be an opportunity to ask our presenters different questions. And if you have questions yourself, please put them in the available box and we'll try to get to them time permitting. So without further ado, I'd like to pass along the virtual microphone to our presenters.
Hi, and welcome to this session. I'm Kayla De La Haye, and I'll be speaking about innovations in research on the social and ecological settings in which people access and consume food, and why this is an important aspect of precision nutrition initiatives that focus on healthy eating from a public health standpoint. I don't have any conflicts to disclose. So as we advance the science of precision nutrition and develop tailored recommendations about what individuals should eat to be healthy, we must also simultaneously advance the science of precision public health nutrition, where we consider how precision nutrition will benefit individuals as well as whole populations, and how to encourage and enable people to be able to eat tailored healthy diets, given the specific social and ecological food systems in which they access and consume food. This perspective is important for a couple of reasons. First, because most people do not follow dietary recommendations, even when these recommendations are quite simple. For example, the American public has been encouraged to eat fruits and vegetables every day for at least a century. The messages have been fairly simple: eat at least 5 fruits and veggies a day, or fill half your plate with fruits and veggies. But the vast majority of people do not follow this simple advice. Only 1 in 10 adults in the US eat the recommended servings of fruits and vegetables. So as we develop the capacity to provide individuals with more tailored dietary recommendations, we'll want to draw on and further develop our knowledge of why people don't eat the foods that are recommended to them for good health. The complex system of factors that influence people's diet and nutritional health is a second key reason to think about precision public health nutrition. Eating is a complex behavior. It's partly influenced by people's genetics, physiology, knowledge, and skills, but it's also very much influenced by economic, social, and ecological factors. These ecological layers are actually best thought of as a complex system with factors interacting across levels to influence what people eat, and also influencing processes that are under the skin. For example, people eat poorer diets and poorer quality diets if they experience food insecurity. And this year it looks like 1 in 4 American households have had this experience. Food insecurity is often caused by interactions between economic stress and poor access to food and physical environments, as well as few resources in one's social environment. Eating behaviors are especially susceptible to these social ecological influences because they're very habitual, meaning that eating patterns are often very automatic and shaped unconsciously by the cues around us. The costs of not seeking to gain a precise understanding of how people's diets and nutrition is influenced by the ecological food system are high. We would likely develop inaccurate knowledge about the role of these complex causal mechanisms in nutritional health, and advances in precision nutrition could increase health disparities instead of decrease them. This is because people with few barriers to eating well will be better able to adopt new and tailored information to improve their diet and health, while those with social, economic, and other barriers, including people with low incomes, those who are food insecure, and people who have experienced discrimination or divestment in their communities, they may not be able to change their diet unless we address the specific barriers they have to doing so. There are many opportunities we can pursue so that precision nutrition is successfully translated to all populations, and especially priority populations. We can draw on innovations in data science, and behavioral and social sciences to gain more precise insights into the social and built environments in which different people acquire and eat food, and richer knowledge of how people's diets and nutrition are differentially influenced by various ecological mechanisms at specific times and in specific settings. And we can draw on this new insight to develop and test interventions that may target individual, social, and ecological mechanisms so that all people can and do eat healthy diets, and so that precision nutrition science is not only effective, but also actionable and equitable. I'll share a couple of examples of innovations in research that examine, with increasing precision, how eating is influenced by social networks and food environments. There's a long history of research documenting the close links between what we eat and our social environments. The people we spend time with and eat with, and the communities and cultures that we belong to influence what we eat. And they encode social rules and social resources that can enable or constrain our food choices. Eating is very much a social practice, and there are now growing opportunities to use new sources of social data and network science to understand more precisely how social exposures and social networks influence what we eat. This research is showing that increasingly we eat in diverse settings and with diverse eating partners as we eat more food away from home, fewer family meals, and eat with more varied people in our social networks, although this last year has certainly been an exception. Across several studies I've been involved in, we've found that on average, people tend to eat food with about 1/4 of the 20 or so people that are closest to them, and they eat with family, friends, and coworkers. But we also find that there is a lot of variability in these eating networks across people and across populations. Longitudinal social network research has shown that nutritional health and our social networks are very interdependent. This is because people tend to select or form social ties with people who are similar to them in terms of health behaviors and health risks. People often connect with others who are similar to them on many characteristics that are related to diet and health, like socioeconomic status and race and ethnicity, the phenomenon of birds of a feather flocking together that network scientists call homophily. Propinquity means that people often form social connections through shared social and physical spaces, at workplaces, community centers, and in organizations. And so they tend to connect to others with similar structural and environmental health exposures. And finally, stigma and discrimination play a role in social selection and the patterning and clustering of health risks in social networks. Over and above these social selection processes, there's also evidence that social ties and networks directly influence people's health behaviors, including their eating behaviors, through many social influence mechanisms like mimicry, normative influence, and by providing social support and social capital. As an example, in this social network study, we found that if adolescents had friends who ate a lot of low nutrient, energy dense junk foods, that they were likely to increase their intake of these foods over the school year. And this effect of network influence was significant after controlling for who the teens selected as friends and their own beliefs about junk foods and their sociodemographics. In another study examining the personal social networks that surround Mexican American adults, we found that more health support in one's social network predicted better diet quality, measured as higher healthy eating index scores. And this was especially true for adults experiencing food insecurity. Overall, we have some insights into a critical feedback loop of social selection and subsequent social exposures that influence diet and health. That's important to account for in precision nutrition research and interventions. Through these social processes, people with the greatest nutritional health risks and inequities are more likely to find themselves in social networks that also confer health risks. and these social exposures can reinforce and influence nutritional health behaviors and be barriers to behavior change, or they can be leveraged as part of network interventions. Moving forward, there are many opportunities to use novel data sources, including surveys and digital traces of social phenomena, to more precisely understand their mechanistic role in diet and nutrition and develop tailored social network interventions. A second area of opportunity for understanding ecological factors in precision nutrition is to more precisely study the food environments in which people acquire and consume food. In the past, this research has looked at what foods people have access to in their home neighborhoods, and sometimes it's looked around their schools and workplaces to understand how those food environments influence what people eat. The results have been mixed, although there is some evidence that more exposure to fast food outlets and less access to grocery stores in someone's neighborhood is a barrier to eating healthy foods. But there are now many opportunities using new data and methods to more precisely track the food environments that people are exposed to. In a new study that I'm leading with Esteban Moro and collaborators at USC and MIT, we're using big mobility data, which is information about people's geolocations captured by their mobile phone. This data is allowing us to analyze the daily movements of over 700,000 Los Angeles residents over a 6-month period. We're using this data combined with point of interest databases to map the food outlets like grocery stores, restaurants, and corner stores that people are close to and that they actually visit as they move throughout their day. This type of data gives us incredibly rich spatial and temporal information for whole populations to answer questions we have about the food environments that people are exposed to and how these influence food choices. We know that 1 in 4 of the 10 million LA County residents live in food deserts where they don't have good access to grocery stores and healthy foods. But our analyses of these mobility data are showing us just how much people move around out of their neighborhoods to get food and where they go to do this. The analysis on this slide looks at visits to food outlets around midday. On the left, we see that the vast majority of Angelenos visit a food outlet that's within 1 kilometer of their current location during lunchtime. But on the right, we find that just a small percentage of the population visit a food outlet at lunchtime that's within 1 kilometer of their home. So we're learning that most Angelenos visit food outlets during the day that are not in their home neighborhood. These mobility data are also giving us insights into how the food environment impacts people's choice of which food outlet to visit. When looking at the whole LA County population and the food outlets that they visit around midday, we find that people have a significantly higher probability of visiting a fast food outlet when they're in a food swamp, meaning a food environment that's inundated with fast food options, compared to when they're in a food environment with less fast food and more healthy options. But we find that the food environment influences people differently, depending on their food habits. For people who rarely visit fast food restaurants over the 6 months that we observe them, the fast food avoiders, I'll call them, they are not more likely to visit a fast food place when they're in a food swamp, unless that food swamp is new to them. In other words, if people who rarely eat fast food find themselves in a food swamp that they haven't visited before, then they're significantly more likely to visit a fast food restaurant. But for fast food enthusiasts, people who frequently go to fast food restaurants, the probability that they will go to a fast food place is highest if they find themselves in a food swamp. And they're actually less likely to go to a fast food place if they're in a novel food swamp that they haven't visited before. So fast food enthusiasts are especially drawn to fast food places in familiar food swamps. So clearly, these examples of research that seek to more precisely understand social network and food environment mechanisms that impact diet and nutrition are just scratching the surface of what is possible. In future, there's enormous potential to gather data that is actively collected from studies, panel surveys, and population surveillance, and integrate this with digital traces that are captured by social media, wearable sensors, mobility data, and crowdsourced information about places and spaces from sources like Foursquare and Yelp. Combining this with census and consumer data and insights from government and community research partners gives us very powerful tools to more precisely understand how social ecological mechanisms impact different people's eating in space and over time. And this can be used to generate new, tailored, in-time, and contextual interventions that draw on this data and mobile technology to address social exposures, food environments, and larger food policies and food justice issues as part of precision nutrition interventions. Thanks very much for attending this talk, and I look forward to our question and answer period.
Hello, I'm Suchi Sare. I'm a professor at Johns Hopkins. Here today I am going to talk about how we can use machine learning and AI to leverage really messy data in order to do learning and inferences. So I work with complex, high-dimensional, heterogeneous, messy, dirty, real-world data sets from electronic health records or wearables. It's the kind of data you might experience in nutrition science. I am not specifically a nutrition science researcher. Instead, a lot of my research involves taking data sets, like I mentioned, in the EMR and in wearables, and leveraging them to be able to do things like early warning for patients at risk for specific diseases, or trying to infer which patients might be responsive to specific treatments, the kinds of questions you might want to ask in nutrition science. So I was asked to come today and discuss example ways in which we can use ML to make useful inferences. And I'm going to talk very quickly about a couple of example works. So the first one here is in Parkinson's disease. One of the big challenges with Parkinson's is symptoms of Parkinson's are very distributed. Symptoms like tremor, rigidity, difficulty walking, loss of balance, and also cognitive in nature. One of the big issues in Parkinson's is right now, today, most of the disease progression actually happens when the patient's at home, but we have no real ability to measure disease progression at home. And it's a very slow evolving disease, and you'd ideally love to be able to track progression, predict patients at risk for deterioration. But instead, the best tools that they have access to today are really when the patient comes in for in-clinic visits. And only way to really even quantitate something is something like what they call a UPDRS, which is a survey-based score. And so here, this was an ambitious, now 6 to 7 year old project. We have a large NIH Center of Excellence that got funded, that's funding some of this work in the last couple of years. The inspiration for this project was, at the time, we had no way to measure disease PD progression at home. So could we use sensors on a phone, myriad sensors that are already available, that are collecting data about movement, cognition, sociability, voice, that could then give us hints into progression of PD. And so when we set out to ask this question, we built this app, we were collecting a lot of this kind of data. You can see the data looks really messy. It's not like the kind of data where it's very clearly, there's one biomarker you can measure, and that biomarker clearly measures and tracks with progression. Instead, you have like, what we had over here was over 250 different very, very messy signals. And then the challenge was, how can we use these different signals to forecast and measure progression? So here what we're showing is across the population, we've taken that data and we've extracted lots of different features. And what we find is basically, indeed, there is signal across different measures we can extract, but no single measure is the gold standard. And second, no single measure is universally good across some patients. So some features are very informative for some patients and other features are very informative for other patients. In other words, we really need an approach to integrate these measures in order to be able to make something meaningful and quantitative and precise that would work across patients. Now, the second challenge and very big challenge we ran into was the idea that at the end of the day, to do any kind of scoring, historically, what we have is either the experts get together and they come up with a quantitative measure, but as you saw, the data were really noisy, so this was super hard to do. So then the only other choice we have is to try to learn or do some kind of inference from the data itself. And very often that means relying on some kind of a gold standard. But here, trying to get neurologists to measure disease progression at home is both very burdensome and expensive and not feasible, really. So what could we have done? So the thing we ended up doing that was quite clever was using a novel machine learning based approach that leverages in the absence of a gold standard, because whenever you're trying to do studies at home, there aren't really high quality annotated data. So here we use some form of like weak supervision, which is basically knowledge of the fact that when the patient was getting medications, and the idea here was that turns out severity of symptom before medication is much higher than severity of symptom after medication on average. So this was an example weak signal we could leverage in order to be able to do learning, and that actually worked quite well. We were able to show that we could recover a score that correlated really well, validated with existing instruments. In addition to that, we were able to, for the first time, use an instrument like this to measure severity on a much, much more frequent basis, in fact, daily basis at home. So here's an example patient we're showing over a 6 to 7 month period. We basically are measuring disease on a daily basis, and we know PD to be highly variable. And what this is showing is in the short term way, like how much variability there is, and in the longer term sense, this patient is pretty stable. Addition to that, here are some examples when, especially in the bottom, where we're showing you a patient where, again, here on a day-to-day basis, these dots are tracking MPDS evolution over time. And at the bottom, we're showing you a patient who actually worsens over time. In the top graph, what we're showing is basically the power of a score of this form that could measure disease at home versus, say, something like a standard clinical instrument, which is shown in green, which is the UPDRS. And what you'd see is like these are both very infrequent, and because there's so much variability, you can't learn very much from UPDRS. Versus with MPDS, it's like easy to see that, the patient in this example happens to be mostly stable. All of this became the basis of an app that is now used by hundreds of thousands of patients on both Apple and Android. So the main takeaway here, there's one big myth around the use of machine learning, or machine learning AI, is like these techniques require large quantities of automated data. Well, it turns out there are lots of different kinds of flexible techniques like semi-supervised learning, unsupervised learning, partially supervised learning that actually leverage really noisy data in very clever ways to be able to do inference. And these are especially useful in examples around data collected in the wild, as we call it, like mobile data at home, where getting gold standard annotations is very, very hard. This is also true in clinical medicine, where very often, even the expert physicians will agree on the diagnosis of a patient. So gold standard is hard. In this case, these kinds of techniques are very powerful. I'll give you a second example very quickly, and this is with EMR data, using that to leverage EMR data and using ML to be able to build real-time clinical decision support tools. So as you know, in EMR data, there are very, very many kinds of structured and unstructured data, like from labs and physiology, which are continuous, which are like streams of signals that are numbers, to tax data. And the question is, how can you take account of this data to be able to build a picture of this patient? How are they progressing? And there's a lot you can do this with this data. Oncology is one of the most exciting places where things are happening, but this is really relevant across every area of medicine. Like the fact that patients are getting treatments and then you're starting to see how the physiology is evolving gives you the opportunity to be able to learn patient-specific response. Like some patients are very responsive to some treatments, but not others. And that, if we can do that well from vast amounts of EMR or observational data, then we really could start to figure out new ways to individualize treatment. And so here's an example where we're using, longitudinal measurements of labs and vitals over time in order to assess. And so here are some technical papers you can read if you're curious. And this has sort of been a topic of study in the last couple of years. And again, very applicable to nutrition science if you're looking to understand the impact of certain foods or certain exercises on, measurable, quantifiable physiology in some way. These kinds of techniques would be very applicable. And so here what we're doing is basically using data to be able to forecast what is this, in the population, what is the variability in treatment response across individuals. And so in this example, what I'm showing you here is different doses. So 3 different medications, the application of these different medications over time, and then its impact on the blood, on the mean arterial pressure. And this is 3 different doses. And each curve here is 1 patient in our database. So what it's saying is, even when you look at pressors, there's lots of variability in treatment response across patients. And similarly on fluids. So what this means is you could now start to think about, in this example where I'm showing you, is 2 different patients. One is very fluid responsive, the other one is not fluid responsive. So you might imagine taking a patient who's not very fluid responsive and putting them on pressors earlier. And so this would be an example of, using EMR data to learn individual specific patient response. Anyway, with that, I'd like to go to my last and final slide, which is AI is a very broad field. Many classes of very productive techniques, including combining mechanistic knowledge with data-driven learning. So it doesn't just all have to be data-driven. There's ways to bring in knowledge from experts. And some of the most exciting results that I've seen come from analysis of messy real-world data sets is when we're able to combine techniques and design flexible methods that accurately account for the messiness of real-world data. So it's very rare that you can just download some off-the-shelf technique and things just work. It's really helpful to be able to, so in other words, if you have a difficult data set or a difficult study, go find another person who deals in data sets of that sort and start brainstorming about other ways in which they can help you leverage, combine or design techniques that could help you, tackle that data set and the messiness of that data set. With that, thank you.
Good morning, everyone, and thanks for being here, and actually thanks for having me here. I'm Chris Hammond, and today I'm going to talk a little bit about artificial intelligence. And in particular, what I'm going to talk about is the notion of the ecosystem, a bit about the ecosystem of AI, with regard to the notion that AI is not a single thing. It's multiple things, and you have to think about it in that way. To give you a sense of context, I'm a professor of computer science at Northwestern. I run our master's program in artificial intelligence and a program called CS+X, which is really the idea that computation is going to impact the world. And so we work on looking at how different fields across the university are impacted today and how we can help with whatever transformations are going to occur. I'm also the co-founder and chief scientist for a company called Narrative Science. And the important thing here is that I take a look at AI from 2 points of view. From the theoretical notion of what is possible, what is doable within the context of AI, and actually from the practical notion of really what kinds of products, what kinds of impact we can have in the world today. So the starting point for this is really asking the question, what is artificial intelligence? And we're going to start with a relatively old school, but I think well understood notion of AI is really the study of systems that do things that, if performed by human beings, would be considered an aspect of intelligence. And the question is, well, what makes human beings so smart? Well, we make decisions. We understand language, which is the thing I love. We draw inferences. We draw conclusions about the world. We can look at the world and recognize situations. We can explain what's happened in the past. We can understand what's happening in the present. And we can plan for and predict elements of what's happening in the future. All of this is driven by our ability to learn from the past, to look at what has happened before and pull out patterns and predictions that we can use to look at the present and the future. So this link between learning and intelligence holds for the machine as well. And if you take a look at everything that's been going on in AI lately, almost all of it is based on a substrate of machine learning. And the question is, well, why today? Why are we seeing so much today? Because for years and years and years, we saw sort of a fallow period in AI where there wasn't a lot of forward movement. But today it's explosive. And that's because we finally have the data that's required for our machines to learn. And now we're in a place where learning is part of the process. For example, think of self-driving cars. Self-driving cars 10, 15 years ago, we would look at that and we'd think this is something that we're not going to see in our lifetimes. But because we started gathering data, and in particular Google gathered data based upon sending cars all over the country, gathering information for Street View, we suddenly found ourselves in the possession of millions of miles of sub-second data of sensors based on sensors outside of a car and the actions taken by a driver. And that is at the core of everything that we're seeing in self-driving cars. Likewise, as we realized that we could start putting sensors on machines all across the world, and in particular in factories, we could start gathering data, and that data could be used to then predict when a machine goes down. Because if you could predict when a machine goes down and avoid the problem of a machine going down in the middle of process, then you can move it out, you can move another machine in, you can work around it. And it improves the entire ecosystem of factories based upon our ability to gather data and actually make use of that data in learning. And finally, one of my favorite examples, the notion of predictive insurance. You've seen the commercials that if you sign up for various insurance companies and you share your data, they'll be able to take all the data they have that is actuarial data, all the data they have that is linked, that links features of behavior to good or bad responses in the world. They could link your data to that and actually tell you exactly what you need to do in order to improve your driving. That is, that they're no longer going to just hedge, be in the business of hedging their bets against bad behavior. What they want to be able to do is help you avoid that behavior and become advisors, become guidance, instead of waiting for bad things to happen. All of these are flowing from the fact we have this data. Well, how did we get here? Where did we get all this data from? Well, we were in an interesting situation, and that is almost every company for a while in the era which we refer to as the big data era, almost every company decided they wanted information. And they sent people out to get information. It turns out getting information is difficult, but getting data is straightforward. It's not easy, but it's straightforward. And so we ended up with masses of data. And this data really takes three primary forms. What we think of as highly structured data, the data that's associated with relational databases. The data around like a sales team, where you could say, in this column is somebody's name, and in this column is October sales. And you can go to that column and find somebody's name in the name column and cut across and the October sales, and that's going to be the October sales for that individual. That is very clear, crisp, clean semantics associated with the data that we have. The second round of data that we have, though, is interesting. And this is high volume, low feature data. It's still structured, but it's things at the level of pixels, things at the level of audio, an audio signal, at the level of all the individual sensor values in a massive array, where any one feature, any one tiny data point is almost meaningless and often can be removed without impacting the entire thing. They only get meaning based upon a larger context. And finally, we have language. That is, we're gathering language left and right, and we have these massive repositories of language that describe things in the world. But the relationship that we have with language is very different than the relationship the machine has with language. And so we're in this situation where we've got these three data sets: structured data, high volume, low feature data, which is the core of what we tend to call deep learning, and then natural language. These are the drivers for AI today, this kind of data. And to give you a sense of how much data we have, we're absorbing about 2.5 zettabytes of data almost every day. My guess is 2.5 zettabytes is not a number that you think of, oh, you know exactly what that means. You're not awestruck by it. To give it a little more context, this is the equivalent of generating and having data for 250,000 libraries of Congress every day. Again, that's still somewhat abstract. To make it really concrete, this is the equivalent at the data level of generating 500 books for every man, woman, and child on the planet every single day. Which is to say, big data succeeded. That is, we're gathering data like crazy all across the spectrum. But if you take a look at how that data is being used and what percentage of it is being used, every single day, a smaller and smaller percentage of it is actually being used by us. Which is to say that big data, while we succeeded in the gathering side, and the utilization side has failed. And data has become the problem. We thought it would be the answer, but it's the problem. But fortunately, the problem itself has empowered the solution, which is to say AI. And what we're seeing is a round of new technologies, suites of new technologies, which are not all the same. And these technologies run from technologies of statistical machine learning, sort of old school learning that we can use to understand things that look like relational data. We can learn to anticipate, to recognize when Bob Smith, our salesperson, is going to make what his sales are going to look like in November if we have his October and we have September and we have August and we have July and we have June coming before it. But we also have this notion of what we call deep learning. Deep learning is completely and utterly driven by data of that second sort. That is data that looks like audio signals, that are pixels, that are sensor readings that tell us what the next step in a self-driving car should be. This data did not really exist for us for a long time, but now we're having it in massive volumes, which actually makes learning possible. And then likewise, evidence-based reasoning, evidence-based learning in many ways. And that is based upon language often. So IBM's Watson system can't actually read and understand the language that it looks like, but it can see patterns and it can look for patterns. And so we can answer questions based upon that data, even though it can't understand it itself. But in order to do that, you need a lot of language. And likewise for these other elements, recommendation systems, the way you use Amazon or Netflix, and you get a recommendation. The recommendation might be perfect, but if you consider how large the set of possibilities are, it's magnificent. This only exists because of transactional data. I know what you've watched, I know what everybody else has watched, and so I can, based upon how similar you are to other people, I can tell you what you might like. I know what you bought, I know what other people have bought, and based upon that, I can tell you what you might want to buy next. All of this is based upon data. And similarly for text analysis and natural language generation. They're all based upon a substrate of massive data sets that we can process. We are now in a world, though, where AI is becoming an integral part of our research ecosystem. It's not just used for practical applications. It's used for us to discover new things, new truths in the world. And so we see machine learning, natural language processing, deep learning, facial recognition, object recognition in general, voice recognition, recommendation systems, all things robotics, including self-driving vehicles, in the entire world of personal assistance, all driven by this data and our ability to use different techniques aimed at solving different problems aimed at that data. And then there's predictive. Now, predictive systems have a special place because knowing what happened yesterday is one thing. Being able to predict what's going to happen tomorrow, be able to predict the impact of certain actions tomorrow, that's something very different. Now, when we're looking at all these possibilities, the question is, well, what do we do in terms of looking at the kinds of problems I have and how to solve them. And there's a trick to that, and that is, don't focus on the technology. Think instead of the task. That is, what is it you want to do? And look at that as a driver, and then look for technologies that are associated with that. Because the task is going to be driven by your research needs. And the task, although it's supported by algorithms and data, it's not the point. I mean, the algorithms and the data are not the point. Solving the problem, getting to the answer, knowing what to do next, that's the problem. And so what we see is that algorithms are instrumental to research. And so the one takeaway I want for you today, for me, is stop thinking about AI as a single thing. Think of it as multiple things, multiple ideas, multiple functionalities. And as you are looking at how to apply them, don't think about trying to apply them because they're nice and shiny and new. Think about the very problems that you're trying to solve and actually aim the technologies at that. Thank you.
Well, thank you, Dr. Delahaye, and thank you, Dr. Hammond. And we're also going to be joined by Dr. Surya. Thank you for those very enlightening talks. And now welcome everyone to the Q&A section, part of section 5, part 1. So as we talk and discuss some of these issues, please feel free to enter your questions into the system, and then we'll try to get to those questions at some point throughout this panel discussion. So maybe we can start, Dr. Delahaye, with some questions about your talk. Very, very enlightening and helpful to understand how these different types of environmental influences and social influences may affect diet and nutrition. So perhaps you could elaborate on what information should we really be trying to capture? Because it can seem like so much, right? You have these complex systems around you, and how do you account for everything that's going on? Where do we start, and where do we actually get this information and data?
Yeah, thanks, Bruce, for the great question. I was thinking about this very issue listening to the end of Dr. Hammond's talk about the wealth of data and little digital traces of information we have that are relevant to thinking about what people eat and consume and how it impacts their health. And how do we start thinking creatively about what the right questions are? I think my experience in my training coming up through psychology and public health was an issue that was raised this morning in the training panel around we often, work from some theories and some traditions and the disciplines that we're trained in and ask a particular set of questions. So for me, it was always thinking about individual factors and beliefs. And, the process of starting to think really creatively about the system and exposure to what some of those interesting questions are. And then also this approach you were touching on of, this bottom up and top down perspective. And so there's going to be really rich insights that come from experts, like in the second talk today, where, we want to draw on our theories and our knowledge and our medical expertise and bring that into the fold. But we also want to get really creative and think, maybe top down and exploratory and what is out there in the data and what sort of signals that we could detect. So from my work in social influence, there's a super fascinating history of research that has put people in labs and watched how they eat when they're with others and when someone's happy and someone's eating a lot versus not. And, what some of this bigger data is allowing us to do is get out in the wild, really observe this maybe at a super
fine-grained individual level where you track a person and really see what their exposures are and who they're eating with. And that might be through sensors or digital technology, but there's also these bird's eye view data that we're using with the mobility data and this population perspective that gives us totally different insights into how things play out over time and interact. So how someone's behavior changes in a different setting or with different people or given the time of day or their history of behavior before that. So I think those are where some of the, I don't know if I answered your first question, but that's sort of where those ideas were taking me today.
Mm-hmm. And you're an expert, a well-known expert in social network analysis and understanding these different types of connections. How broadly should we go in terms of like figuring out these connections and how people are connected? Because in theory, people on a given day can run into many different folks.
I think some of those questions are unanswered. I mean, we have an understanding that the social ties that we're really embedded in, so the constant exposures of our family ties and close friends, they have very strong influences on our knowledge, our beliefs. They unconsciously cue our behavior. And so, if we're thinking about a nutrition intervention, someone might be able to change their behaviors for a few months, but what is very common is that it's very hard to sustain things that aren't supported by your social and larger environment. And so, those close social ties, interventions might look like more group-based things, more things that explicitly target people in your networks. And I think we don't really have a good understanding yet of how much that scales up and out and what are some of the bigger phenomena that occur because of this. So, if I go and eat at a certain place at lunch every day, are the sort of norms that everyone orders a salad or everyone gets burgers, is that cueing me because there's certain types of people there when I go and eat? Is what's normal in my neighborhood and community and sort of these more infrequent social exposures also playing a role? And are those going to be meaningful barriers to someone changing their behavior or not? So I think some of that research is still things that we need to look at.
Thank you, Dr. Zilla. Hey, Dr. Hammond, great talk. And I know you mentioned, a key point at the end, like don't start with the technology, because many times, I'll hear the phrase, oh, I want to use AI, period. And then find me a way to use AI to address nutrition, or find a way for me to use machine learning to address nutrition. Could you expand on, you said you start with the problem, you start with the issue, but say someone has an issue or problem, like at what point should they determine how to engage or use technology? Maybe you could elaborate on that a bit.
Well, I think particularly when we're looking at the world of AI, and most particularly when we're looking at machine learning, the question really comes down to if you've got a task in front of you, what that is really associated with understanding a piece of information. So when it comes to people understanding nutritional issues or people being responsive, there's the what are the apparent causes? Questions about that. Are they local? They're seen as an ecosystem? What are the factors that are going to give rise to somebody doing performing behaviors that they don't want themselves to do, you don't want them to do, no one wants them to do. But then there's the other side. It's like, well, how do you intervene? If you've established what the behavior, what the causes are, how can you actually build up the information that is necessary to understand how do you change those? So for each one of those, it's a different question. It's a different line of research. It's a different piece of work. And then as you look at that, it's like, all right, do I have the data available to me? That if I had all the time in the world, given the data that I have, would I be able to sift through it and figure out what the causation is? Would I be able to sift through it and figure out where the interventions lie? Would I be able to sift through it and see what the dynamics look like for any given individual? And if the data are available, then you start thinking about, okay, what's the nature of that data? So if we're looking at data that's coming from conversations have on social media, well, that's not something that you can just take a nice statistical approach to and tie feature to response. You need to do something that deals with, you need to do something that deals with the ambiguity of language and how 5 different ways of saying the same thing are still ways of saying the same thing. So there's a technology you need there just to get yourself to a data set that the machine can use reasonably well. Once you converge on well-structured data, well-understood data, unambiguous data, then you start using the techniques, the standard techniques from statistics, the standard techniques from now AI in machine learning and deep learning, depending upon how large the data set is. If I have a data set where each example has 10,000 inputs, we're going to go a neural net direction. If the inputs are 20, I could actually probably use something that looks like relatively standard regression analysis. And it comes down to realizing that the task defines everything, the problem defines everything, and then you look for the data, and then the data defines a new set of things. And for each one of those steps, you have to wait until you know the answer to the nature of the task, the nature of the information need, the nature of the research, the nature of the data, before you can start making algorithmic decisions. But once you've made those decisions about, or once you've gathered that information, those algorithmic decisions are relatively straightforward. And the problem is that what we see over and over again, and the way I like to think of it is, even 5 years ago, if you wanted to use a deep learning model, you had to go find yourself a PhD in computer science and talk to them. Today, you need a credit card. And you get yourself an AWS account and you start running things. And you might be using exactly the wrong technology. You can do it. But if you don't understand the nature of the data, the nature, how clean it is, how dirty it is, how well it's normalized, how it's been enriched, all those things, you will make mistakes. And you will learn things that are not true. Because the data by its nature, messy and ugly as it is, because it's hooked to the world, will lead you down paths. So,
Bruce, if you'll allow, I would love to build on what Christian said and maybe even disagree with him a little bit.
Mm-hmm. Yeah, absolutely. In fact, I was going to ask you to comment on Dr. Hammond's comment.
Yeah, so I do agree with Christian that, and am I pronouncing your name correctly, Christian?
It's Christian. Okay. It's as though I had religious affiliation.
Got it. Perfect. So I think I agree with his point that you have to start from the problem. The biggest mistake people make is not starting from the problem and trying to figure out what's the problem they're trying to solve. The second thing then they need to do is collect data, which is intuitively what any responsible scientist would do. However, the reality is, we all start by writing grants. In other words, our grant has to have the problem, the data collection strategy, and the approach all defined before we actually do any data collection for real. So I think after you have the problem and you have some notion of like, here are candidate data sources, I think that's where I'm going to now diverge. So to me, one of the big things that's been possible over the last 10 years is many, many more learning strategies are now available online. You can just download it and run it and get some output, which means you naturally open yourself to many more situations, like he said, where you can just get garbage in, garbage out, and then you can make conclusions that are garbage. So especially when we go to real world data, as soon as we're going to messy environments, real world data, what I find in practice is that the answers are not straightforward. The algorithmic choices are not straightforward because the data are messy. So in reality, I very rarely see that it's just I, as a practitioner, can just get my problem defined, get my data, and then I know how much money I need, so I can just go buy deep learning. If it's a big data set versus a small data set, then I buy this. That's not my experience. My experience is, in reality, real data is complicated. There are lots of biases you have to account for. There's lots of dependencies. It depends on the question. If you have small data, machine learning and AI can be applied very effectively if you have the right tools at your disposal. So in reality, at that point, my thought would be to either use your own knowledge, do a bunch of reading, and find other experts in the field with whom you might have a strategy discussion. And in that strategy discussion, one thing that's very important is to think hard about their ability to engage with your problem and with your data. Because if they give you a strategy where they have zero understanding of your data, zero understanding of the complexity of your data, and zero understanding of the problems with your data, then that's not likelihood you're going to employ a terrible strategy and you're going to get garbage output. And there are a fair number of bad ML practitioner papers like that, where somebody went in, they downloaded something, they deployed something, and they wrote like a paper that wasn't very high quality. And then that leads to your classic media newspaper preprint that says, hey, look, this model is garbage and the outputs are garbage. Anyway, so that sort of would be my takeaway. Find an expert practitioner with whom you can brainstorm strategy and gauge their ability to indulge with your data, the complexity of your data and your problem in coming up with a strategy. And then ideally, the answer is as simple as stitch together these commonly known things, or you might have to design something in your scenario. A lot is possible now with real world complicated data with the right strategies. A lot more than was possible before, when we just had access to only very simple strategies.
So that, Dr. Sari, that brings up a question.
One quickie. In seemingly disagreeing, we are in agreement 1,000-fold. I think one of the things that people really don't understand is that they will often find themselves with a data set, and they've been told all sorts of wonderful things about the nature of the data set, how rich it is, how complete it is, how well distributed the examples are from it. It is almost never the case that is real. My favorite example of this is that there's a data set associated with fires that was aimed at looking at fire prevention. And if you take a look at the data set, it turns out that almost all the fires in Boston are kitchen fires. And the reason why almost all the fires in Boston are kitchen fires is because the form that you use to fill out your report, if you say it's a kitchen fire, there are 5 pages of other aspects of the problem you don't have to ever touch on. So it's easier to say it's a kitchen fire than another kind of fire, which means that people are incentivized to say the wrong thing. And you have to go down all the way down to that level of where was the data source? What are the incentives associated with the individuals who are putting that data in, if there are people involved? And then if it's sensors, what's the fidelity of the sensors themselves? I mean, it's data is everything in this world, and it is shocking how bad it is, how faulty it is, and how much work we have to put into it.
Excellent points, and I learned a little bit about kitchen fires. So I guess the question is for all three of you, so several things. So one is, we know that a lot of the paradigm is people will collect data, either through they'll have a ongoing cohort of people or what have you, or they'll have a data set they're just building, and they'll say, okay, now I've got the data set, then I want to pull out inferences from this using different types of techniques. So maybe if you could comment on how that may need to change, and also, do we need to change the questions that we're asking? Because Dr. Sari, you mentioned that many times with grants, you're forced to have a very precise question, and that comes from before, where you have a clear hypothesis, and then you test it, and then you have the answer. But we're clearly in a different situation where we're trying to untangle these complex questions or complex answers as well. So how do we change the nature of investigation and research and scientific questioning, given the fact that we have new types of data and new types of analytics? Dr. Sari, and I'd like also comments from Dr. Delahaye and Dr. Hammond as well.
So I think a couple of thoughts there. So the first thought is I still think we need to understand the question we're asking. We still need to understand the problem we're solving. It's just that the nature of the question and the nature of the problem changes. So for instance, previously, So I think when you don't know what the question is, or what you don't understand what the problem you're solving, then you're just hunting in the dark and you're going to be lost. So I think that never goes away. Any scientist, part of any scientific curiosity is kind of even knowing what is it that you're trying to do. So in terms of the nature of the question itself, I think what I found is you can ask far more ambitious questions. So an example, just going back to one of the examples I shared in the presentation, historically, a simple question you might have asked is, I have found patients in the lab, I measured, this particular, I put like a sensor in the thing and I measure in 1 minute if they move in this particular way, does that particular, movement of the finger associate with the severity of Parkinson's as measured by UPDRS? It's a very narrow question and a very narrow specific question. I can ask much bigger, harder questions. If I were to collect these 250 measurements, can I integrate them to develop a progression measure of Parkinson's? Like, the nature and ambition of the question is much bigger, harder, because there are many more strategies available to you. The second thing that I've discovered over the course of the last, as I've interacted with collaborators in many different areas of medicine in particular, is that I think scientists who are used to operating a certain way, over time your brain learns to ask questions you know how to respond to. So you precondition your brain, where if you spend like a good third of your career answering questions of the kind where if I measure this and I measure that and I want to report the association between those two measurements, then that's the question your brain will ask and want to answer. Why? Because it thinks it's not possible to do more than that. And this has been countless times I've observed this, where I've been in scenarios where there are some really cool questions you can ask and answer that would be very, very meaningful. But to get to those questions, it required a fair amount of jostling and back and forth, and the ability to debate and question each other and push back. Because when somebody, to me, a domain scientist, presents a question, I often want to know, are you telling me you want to solve this question because it's the one you know how to solve, or is it because the question we truly care to solve? And then we go back and forth in defining the question, which, let's say you had a magical one, what's the question you'd want to solve? And then can we design a strategy? And so then that, to my last and final takeaway there is, I've been continually impressed by how often it's possible to design interesting new strategies to pull information out of data when commonly you would think to have thrown up your hand and said it's not possible. Like, I actually think there are many more things that are possible than not possible. So, and I wouldn't say this to an irresponsible room of like people where they don't understand any stat, any math. They're just like going wild with random code. But I'm assuming like you understand stat and math and code, and you have the ability to think carefully and smartly and all that good stuff. Then I'm saying I've been continually, like in my experience, 9 out of 10 times the answer is not, it's not possible. 9 out of 10 times the answer is, it's possible with the right strategy. So I want to condition people into thinking it's possible with the right strategy. Now we'll find somebody to help you with coming up with the right strategy.
Dr. Delahaye and Dr. Hammond, any thoughts?
Yeah, I think my experience with this process of coming up with the right questions and then how do you translate that to useful science, that those conversations take a lot of time. So these types of interdisciplinary teams where, so one example is this year I've been doing more work on food insecurity and the impact that's having on people's diets during the pandemic. And we early on put together an interdisciplinary team, but it's a lot of conversations about, okay, what data do we need? What should we survey people on? I didn't even imagine some of the data that was out there that might be useful for us that came about through pretty iterative conversations with geographers and physicists and data scientists. And they said, oh, what about this? If you're trying to understand that feature, I think this could be useful. And I think one of the challenges with that process is funding mechanisms. And, you're not going to be writing that grant with the specific detailed analytic plan, in month 1. It's going to be my experience, especially in eating behavior work, is that process could take a year. So it may be pilot funding or other types of smaller things to have that iterative. And then one other point I want to make with that experience, I think, is that often I've found that we are trying to find complementary data sources. And so it may be, that there's a big scale, pattern or scope that we want to understand what's going on with the population. And there might be some existing big data for that. But also we need to maybe go out and collect interview data and surveys and try to understand what we're missing, what's not captured in some of the features. Are there whole populations that are missing from some of the big data that's there that we're not seeing? What does our community partners say? And they often provide us with really, valuable insights about what we're not thinking about or what's not captured or issues in that data. And so I've been thinking a lot more about this as like, there's all these pieces of a puzzle, and one of the big challenges is not just the analysis of each of these components of the system or the system of a whole, but how do we, usefully piece them together for the questions? And what are those questions? To me, that is a really creative process that changes and evolves through this.
Mm-hmm. And I absolutely agree with the notion that we sometimes find ourselves trapped in our own science. That is to say that we have an idea about what constitutes an appropriate question, what kind of answers that we're looking for. I think it's particularly deadly when you have a focus on what you're trying, in some sense, what you're trying to prove, because there are many, many strategies out there that can be applied to a given data set, and some of them will allow you to prove whatever it is you want to prove, and some won't. And what we see is people converging on the ones that will help them confirm their point of view. And so I think that although once you know what question you want to have answered, that clarifies and makes the computational side of the equation go faster and easier. But there is that notion of using learning techniques, not simply to answer a single question, but actually sometimes to begin to elevate the possibilities. And I actually really love the notion of thinking about this in terms of the world of the possible. What could I ask? Or what could I possibly know? And then doing things experimentally. And the problem, the danger there, though, is that sometimes you'll get something that looks like an indication of a direction, and people get confused and think that that's still an answer. And it's like, no, that's the place where now you've got to clarify the data. You've got to make decisions about how good or bad it is, whether or not it's just there to support your point of view. But I think that using AI not just as a tool, for pure question answering, but again, the nature of the task. Part of our task is exploration, and AI can help us there as well. Machine learning in particular can help us there as well. As long as we start thinking about building systems that we can have a relationship with. It's not just, there's a data, I build a model. There's a data, I build a model, I can interact with the system that's building the model. I can interactively choose features, choose focus, direct the system, and let the system itself tell me from the data that stands what can be known from it. And that's actually, oddly enough, that's kind of what I do, is look at exploration and building intelligent systems that help you explore, not just do the pure machine learning to answer questions.
Okay, so in the final about 7 minutes of our session, I'm going to go to some of our audience questions, and we'll try to get through as many as possible. We certainly could be lots of stuff to talk about, so we'll see how many we can get through. So the first question is, once data is well defined and unambiguous for the task at hand, can you reuse the data for different tasks, or does every new task require a new well-defined data set?
Yes.
Next question.
Yes, as long as it's relevant to the other task.
Mm-hmm.
Well, I have a bit of a disagreement with that in that, so say when we're trying to understand eating behaviors and we're identifying these data sets or streams that are useful, there's a data infrastructure there that's reusable. And so like a knowledge that we've gained about signals in certain data sets or how they become integrated, that gets carried forward and reused.
Okay. And then this next question is specifically to you, Dr. Delahaye. Describe the data acquisition process. What government entities or companies or individuals do you work with to get such data streams?
So this has been a big challenge, and just like kind of working out, I mean, for someone who's more in behavioral sciences, learning what's possible with data and what some of the challenges are from computational social science and data science folks. There's a lot of data we draw on that's publicly available. So information from Yelp, for example, about food outlets and food environments, or government databases of these types of places. Information about, say, mobility or people's social networks that are available on social media databases. These are things that require often negotiations or data use agreements with companies, and that changes over time and can totally disrupt people's research agendas. There seems to be this year with COVID and the value that's seen in some of these data sets, like an increasing systematized effort to make it available to researchers. And so, for example, with the mobility data, SafeGraph has made a lot of that data available for research purposes where it's aggregated at a census tract level. So it's de-identified, but it's still highly useful. And the best experience I've had with this is working with an office in our university called the Public Exchange, whose whole job it is to help researchers make these public and private partnerships and identify, collaborations with Yelp or collaborations with other companies that might have some of the information that we want to try to draw on. But yeah, that is a challenge and time consuming.
I guess this question is actually a follow-on both for you, Dr. Delahaye, and as you as well, Dr. Saria. How are you obtaining informed consent and protecting the privacy of participants while collecting mobility data?
Should I go first?
Maybe you could go first. Yeah.
Yeah, in the data that we collected in PD, where we had where we did get consent, when they download the app, they get a protocol. They had to download an app. In order to download the app, they effectively get a questionnaire that describes sort of what the study does, and explicitly asks for, describes what they'll do with the data, and for the permission.
Yeah, my experience is the same. So when it's more like experimental studies where we have apps that we've designed and we're sensing people's eating behaviors or social phenomena, then they go through that same sort of protocol. And then for these larger scale data sets, it's, utilizing data where they only share the data where someone is consented to have that data utilized from their phone and shared to third parties.
Another question there, and Dr. Hammond, maybe you could address this. What are the numbers that you need for AI? What kind of nutritional or health data could you use for AI? So it is a general question, but maybe you could offer some thoughts on that.
There's two components. The numbers is a technical question about that's really based upon what you want to learn. How many features are in the data, individual example, how many examples that you have. And there that the devil is in the details. On the other side, it's more a domain question. If you're looking at any domain, again, the question comes down to what do you want to know? And what you want to know defines the data that you're going to need in order to know it. And if it's a relationship between environmental factors, location, demographics, and eating behaviors, then you need to have both sides of the equation. You always need both sides of the equation at some level, because the reality is what you're trying to do with any machine learning system is you're trying to take a set of features that are visible in the world and infer a feature that is not yet visible in the world based upon looking at examples in which you had both sides. You had the hidden feature that you care about, and the visible features that you can use to infer it. But that's really, it depends upon what the nature of the question is, and the nature of the domain. And I'll tell you, the number question is an interesting one, in that in fact, I have a group right now that's looking at trying to get down to the very specific formula for different algorithms, based upon what is it you want to know. And that is it a binary relationship? Is it a label with multiple possibilities? And then, given on the data side, how many features could be predictive of the thing you want to know? How many, and what the distribution of the examples really end up being across the population you care about. And if you start gathering that, then you can get to something that looks like a real equation, and that tells you this is the number, this is the volume of examples you need. And the thing that actually continues to surprise me is that the answer to that question is usually a lot, which is not a particularly computational answer. And it's because there hasn't been enough work on really getting to the details of that formula.
Okay, I'm going to wrap up with one more question and just a wrap-up statement. So, data science approaches allow us to obtain clusters of people with certain phenotypes, and are often association studies. Could we comment on whether the need to test the simulations or things that we gather from different data science approaches or techniques how do they need to be tested in clinical trials to confirm the evidence generated from the data analytics? So basically, seeing how this fits in with clinical trials and other types of methodologies.
I view it as complementary. So there's, insight we'll gain from more analytic approaches, from natural experiment data that might be available in some of the data sources that are out there. And then, often at some point we need to try to change the thing that we're, suspecting that is the mechanism or the change process that we're most interested in. And if anything that I've learned in health behavior interventions is that the things that predict the behavior aren't always the things that are going to change them. And so if we're thinking about this from an intervention standpoint, from nutrition, there's probably going to be a lot of complementary work that tests this through trials or natural experiments or other simulation processes like the ones that you brought up, Bruce, around what the world of possibilities and the most likely potential change process that we should be narrowing in on.
Dr. Asaria, any thoughts?
I think it's exactly what was just said, which is in reality, I think we have the problem, we have the data, then we have a strategy for approaching inferences. I would say just as important as the fourth part of it is how are you going to validate or how are you going to interrogate whatever you've discovered. And again, the thing that's really cool in practice is historically people in medicine have thought about clinical trials as sort of like the gold standard. And I think increasingly even, real world data and how that's informing strategies for drug development with the FDA. So I feel like there are many more novel strategies now for drawing inferences that are reliable, but you need the right kinds of validation strategies that are creative to ensure that you can actually measure that whatever you're claiming is working is indeed working. And so in other words, the more confidence you can build in a high quality validation strategy, the more flexible you can be in both the questions you can ask, the data you can use, and the strategies you can use for inferring them.
Dr. Hammond, maybe 30 seconds of your thoughts?
I mean, this is always an issue when you're doing anything statistical. You get these lovely correlations, and now you've got to get to causation. And the way you get to causation is one way or the other. You're going to have to do some sort of experimentation. That experimentation, to the last point, that experimentation can take the form of a new way of looking at the data, but clinical trials is one possibility. But I think the more, as we get more and more data, the possibility of actually finding other validation techniques using the data layer itself makes a ton of sense.
And I'm going to toss in some of my thoughts. I feel that these different types of analytic approaches can also be used to help design clinical trials and guide how these are actually executed and what information is collected. So it's actually an iterative process where clinical trials can feed onto the analytics and all the other methodologies, and you can go round and around and get an approach to the solutions or the answers. So unfortunately, we're out of time, and I know there were lots of other questions. So what we'll try to do is certainly try to address some of these other questions later on throughout the day. I and my two co-chairs for the meeting will be having a wrap-up session at the end of the day at 4 o'clock. So for those of you who ask questions, we'll try to address some of those questions then as well. So that's also a plug to stay on throughout the day and see our session. We're very fortunate to have been joined by 3 world leaders in terms of different types of data analytics, computational analytics, system science, social network analyses, et cetera. So, thank you, Dr. Saria, for your time. Thank you, Dr. Hammond. Thank you, Dr. Delahaye. The work that the 3 of you have been doing has been exciting. We're at an exciting inflection point in precision nutrition and really anticipate great things out of your research going forward to help inform not just precision nutrition, but also health in general. So thank you for joining us. And for everyone else who's watching,
thank you.
So the next steps is we have a lunch break. You can always visit the poster sessions. You can visit the virtual networking lounge if you'd like to. And we're going to resume our talks and our panel discussions at 1 o'clock. And the next section will be focused on translation and ethics. So when you talk about computational and data analytics, how do you actually translate that to policy making, to decision making, to understanding of by the general public, and also what are the potential ethical challenges and dilemmas? So please join us for that. Nico Pronk and Brennan Perrin will be leading us off with their talks, and then we're going to have a panel discussion afterwards. So once again, thanks for joining us, and please stay on for the rest of the day.
Thank you.